Hello friends, welcome back. In the second part of the lecture entitled Engineering Disordered Fibrous Materials via Theory of Fiber to Fiber Contacts, we are going to look at the fiber to fiber contacts in random fibrous assemblies. So, how we can calculate the number of fiber to fiber contacts and the distance between the contacts in random fibrous assemblies. As we discussed in the first part of the lecture, that there are 4 different kinds of fibrous materials or 4 different kinds of fabrics. As you can see, A is a woven fabric, B is a braided fabric, C is a knitted fabric and D is the non-woven fabric. And you can see that A, B and C fabrics are regular structures, where the distance between the consecutive yarns is quite regular and is quite fixed. For example, in woven fabric, the distance between the yarns is fixed, and similarly the distance between the yarns in a braided fabric is also fixed, and the same goes for the distance between the yarns in a knitted fabric is also quite fixed. However, in case of a non-woven fabric which has randomly aligned or anisotropically aligned fibers, the distance between the contacts is varying within the structure. As you can see, for example, the distance between these 2 fibers is not same as that of these 2 fibers. So, it is varying within the structure. So, the distance between the fibers is varying within a non-woven fabric, and if you are supposed to calculate the mean distance between the contacts, then you can simply take the average. But since the structure is highly voluminous in nature, we do not know the distance between the contacts in the bulk of the assembly. Therefore, we need to calculate the mean distance between the contacts with the help of the fiber volume fractions and the fiber diameter. So, as you can see, non-woven fabric is a highly disordered system. There is a need to understand and to compute the distance between the contacts and number of fiber to fiber contacts. In this regard, Van Wyck was one of the first researchers who developed a model for compressibility of random fibrous assemblies, and here he used a disordered fiber system, which you can see here, and a fiber which is shown here with the help of a circle. This is a cross section of the fibrous assembly, and this fiber is actually creating a force dF on the other fiber, which is shown here with a purple color, and it creates a deflection dy. So, using simple theory of elasticity, he calculated the force which is required to create a deflection dy. Here he made use of a beam constant, depends what kind of beam would you like to take, then I, area moment of inertia, then y, Young's modulus, and b bar cube, where b bar is the mean distance between the fiber to fiber contacts. So, one of his major contributions of his research work was to calculate the mean distance between the contacts in case of random fibrous assemblies. So, in this lecture we are going to focus how to calculate mean distance between the contacts using Van Wyck's work. Since Van Wyck was working on wool fibers, so he developed a model for the wool fibrous assemblies, and in this case he considered the wool fibers of diameter d confined in a cylindrical container of unit cross section, and let the height or volume be V. Since the cross sectional area of this cylinder is unity, then one can simply say that volume is equal to the height of the cylinder. Now, consider a spherical particle of same dimensions as that of fiber diameter moves vertically in the container, and this is shown here with the help of this sphere of diameter d. Okay. So, if we are supposed to calculate the number of times that the particle hit a fiber, so this fiber is shown here with the help of pink color cylinder. So, if we are supposed to calculate the number of times that the particle hit a fiber, then we have to make use of geometrical probability. And how? We have to calculate the effective area presented by such fibers to the total cross sectional area of the bigger cylinder, which is unity. So, in this case the main aim is to calculate the effective area presented by the fibers. So, the effective area presented by the fibers to the center of spherical particle without considering the randomness of the fibrous material would be 2 LD. If L is the length of the fiber which is confined in this cylinder and D is the diameter of the fiber, then it will be 2 LD. Why 2 LD and not LD? Because a collision between the particle of same diameter as that of cylindrical fiber will only occur when the center of the particle approaches within a distance d or the diameter of the fiber axis. So, you can see this distance is d. So, when a particle comes in this region, then apparently it makes a contact with the fiber. So, here the spherical particle is considered, which is also representing another fiber, but just for simplicity Van Wyck actually considered the spherical particle in place of cylindrical fiber, but both these entities are having the same diameter. So, in this case the effective area, as you can see, presented by the fibers is 2d L. D is the diameter of the fiber or the diameter of the particle in this case, because both are same, and L is the length of the fiber. So, this is the effective area which is effectively presented by the fibers to the center of the spherical particle. So, the effective area presented by the fibers to the center of the spherical particle without considering the randomness of the fibrous material would be 2 LD. So, in order to incorporate the randomness of fibrous material or the random orientation of fibers, the number of collisions would depend upon the effective area of the fibers projected on a horizontal plane. So, in this case what we do is we actually consider the fiber on a spherical coordinate system, and if theta is the angle between the fiber element and the z axis, then the area of the element must be multiplied by sin theta, because it is projected on the xy plane, because we would like to calculate the effective area on the horizontal plane. So, here we have considered a sphere of radius r, okay, and phi is the azimuthal or in plane orientation angle of the fiber. Okay. So, this is the angle made on the xy plane. So, if we consider the r as a radius of this sphere, then apparently the area of this element would be obviously r d theta multiplied by r sin theta d phi, which will be r square sin theta d phi. But when it is being projected on the xy plane, it would be again multiplied by another sin theta, which will give us r square sin square theta d phi. But since this radius is unity, then apparently you would be left with only sin square theta d phi. This is the area being projected on the xy plane. So, if we are supposed to calculate the effective area presented by the fibers, we must calculate the projection of the area which is on the xy plane with the help of spatial averaging. So, suppose the length of the fiber L is divided into infinitesimal equal lengths, the projection of the area element would be 2 LD as we have calculated earlier into the mean of sin theta, which is the spatial averaging of sin theta, and the spatial averaging of sin theta can be calculated with the help of the area which is being projected here on the xy plane, which is sin square theta d theta d phi. Since our integral limits would depend on the angle theta and phi, and on the basis of spherical coordinate system it would be 0 to pi for theta, and for phi it would be 0 to 2 pi. So, we average it out with the surface area of the sphere, which is 4 pi, because r is unity. So, in this case we are going to get the value of pi by 4. So, spatial average value of sin theta would be pi by 4. So, the effective area presented by the fibers to a vertically moving spherical particle would be 2 LD into pi by 4, which is pi L d by 2. L is the length of the fiber contained in a cylinder, d is the diameter of the fiber. But we also need to know how many number of times that the particle would strike a fiber in travelling a distance or a height v, because volume is same as that of height, which would be calculated by simply taking the ratio pi L d by 2 v, which we have calculated earlier. But once we know that how many number of times the particle strikes a fiber, then apparently we can calculate the mean distance between the fiber to fiber contacts, which is represented here by b bar, which is just the inverse of this expression. So, the mean distance between the contacts would be a function of the length of the fiber, which is confined in the cylinder, d is the diameter of the fiber, and v is the volume of the cylinder. Now, using the expression of fiber volume fraction, which is the ratio of fiber volume, which is pi d square L by 4 to the total volume of the fabric, or the total volume of the cylinder in this case. So, Vf is the fiber volume fraction. So, we can actually translate this expression or the equation 1 in terms of fiber volume fraction. So, if we combine equations 1 and 2, we get b bar simply as a ratio of the fiber diameter, or the you can say or the fiber radius, because it is d by 2, and the fiber volume fraction. So, we can easily calculate the mean distance between the fiber to fiber contacts in terms of fiber diameter and the fiber volume fraction. So, this is a simple formula to calculate the mean distance between the contacts and number of fiber to fiber contacts per unit length, because if we inverse b bar, then we will get the number of fiber to fiber contacts per unit length of the fiber. So, let us take an example how we can actually make use of this formula to calculate the mean distance between the contacts and number of fiber to fiber contacts per unit length. So, the first example is a random fibrous assembly made up of polypropylene fiber of diameter 40 micron has a mass per unit area of 200 gram per meter square and thickness of 2 millimeter. Now, we are supposed to calculate the mean distance between the fiber to fiber contacts and number of contacts per millimeter length. So, we are going to make use of the formula which we derived earlier. Since we are supposed to calculate the mean distance between the fiber to fiber contacts, then it is a function of the fiber diameter and the fiber volume fraction. Here the fiber diameter is given to us, which is 40 microns, but we are supposed to calculate the fiber volume fraction. And we know that fiber volume fraction is a ratio of fiber volume to the fabric volume. So, fiber volume is mass upon density and fabric volume is area into thickness. So, mass per unit area, we also call it as GSM, is defined by W here, and we divide it by the thickness T and the rho f. Rho f is the fiber density. So, we can also calculate the number of fiber to fiber contacts per unit length, as we have discussed earlier, by taking the inverse of B bar. Now, we are ready to solve this problem since we have all the required formulas. So, now we change all the units into SI units. So, the diameter of the fiber would become 40 into 10 raised to minus 6 meter. We also know the density of polypropylene fiber, which is rho f, which is 910 kg per meter cube. So, we can also convert the mass per unit area in terms of kg per meter square. We can also convert thickness in meters, which is 2 into 10 raised to minus 3 meters, and now we put all these values, the mass per unit area, thickness and the fiber density, to calculate the fiber volume fraction, which comes out to be 0.11 here. And once we know the fiber volume fraction, we can also calculate the mean distance between the contacts with the help of fiber diameter and fiber volume fraction, which comes out to be 181.8 microns. So, accordingly, the number of fiber to fiber contacts per unit length, in this case per unit meter, it is 0.0055 into 10 raised to 6 contacts per meter, or number of contacts per millimeter length would be nearly 6. So, you can see for 1 millimeter length of fiber, there are nearly 6 contacts being made, and you can also see the mean distance between the fiber to fiber contacts to be 181.8 microns. So, with the help of fiber volume fractions and with the help of fiber diameter, we can calculate such complex parameters which are not easily measurable. So, let us take another example. A random fibrous assembly made up of polypropylene fibers of diameter 30 microns has been compressed by 50% strain in a confined container, neglecting any changes caused by the sides of the container. Calculate the mean distance between the fiber to fiber contacts and number of contacts per millimeter length when the compressed fiber volume fraction is 10%. So, now we are supposed to calculate the mean distance between the fiber to fiber contacts when the random fibrous assembly is being compressed by nearly 50% compression strain, and we also know the compressed fiber volume fraction is 10%. So, since the compressive strain is known to us, so we know since it is compression, so we have just changed the formula of compression strain in terms of the ratio of the change in thickness to the initial thickness. So, change in thickness, if you normally calculate the strain, it is normally with respect to the final entity, but in this case it is a compressive strain. This is the reason we have considered T naught as the first entity, and then so the change is T naught minus T f by T naught, which is given to us 0.5, where T naught is of initial thickness, T f is the final thickness. Since we have mentioned that we have not considered any changes caused by the sides of the container, then in this case we can neglect the Poisson's effect. And in such a scenario, we also know that the T thickness of the fibrous assembly is inversely proportional to the fiber volume fraction. So, in this case we can replace T with the Vf and we get a new formula out of it, and you can see it is Vf minus Vf naught by Vf. So, Vf naught is the initial volume fraction that we are supposed to calculate. So, as you can see, we can rearrange this equation. Vf naught is equal to 1 minus delta epsilon Vf. So, we can calculate Vf naught because final fiber volume fraction is given to us, which comes out to be 0.05. So, this is significantly important for our calculation because we are supposed to calculate the mean distance between the fiber to fiber contacts on the basis of initial fiber volume fraction. So, since we have used this formula earlier, we can calculate the mean distance between the contacts as the ratio of the fiber radius and initial fiber volume fraction here, and we get the value of 300 microns. And once you inverse this value of B bar, you can get the contacts per millimeter, which is 3 contacts per millimeter. Now, we have completed this part of the lecture, and in next part of the lecture we are going to discuss the anisotropic fibrous assemblies, how we can actually calculate the number of fiber to fiber contacts, how we can calculate the mean distance between the contacts, and later on we will be talking about the application of fiber to fiber contact theory in regard to the properties of these materials. Thank you very much.